The idea that the universe must have an edge appeared long before the invention of telescopes. Human perception naturally seeks completeness. If there is space, the mind expects an ending, a boundary, a final point. But modern cosmology reveals a very different picture. The boundary of the universe may not be a solid physical barrier, not a wall, not a shell, not a surface you could ever reach. Instead, it may exist only as a mathematical concept, a limit that defines how far light can travel, which events can ever become visible to us, and which horizons remain unreachable for fundamental reasons. Observations show a universe that has been expanding for more than 13 billion years. Yet time alone does not tell us how far the limit truly is. Light from the most distant regions does not arrive from where those regions were when it was emitted, but from where they are now after space itself has stretched and grown. This creates a strange and almost paradoxical experience of space. We look into the past, yet we observe regions that today are tens of billions of light years away. When these distances are written out in full, the number becomes almost impossible to grasp. The observable universe spans more than 90 billion light-years across. The mind struggles with such scale, but this number defines the true size of everything that is accessible to us. The boundary of the observable universe is not the actual edge of all existence. It is simply the limit beyond which light has not had time to reach us, even while moving at the ultimate cosmic speed. You can imagine a vast sphere inside which lies everything capable of sending us information. Beyond this sphere, space may continue uninterrupted, galaxies forming, stars being born, densities fluctuating. Large-scale structures evolving quietly in the dark. Those regions remain hidden because their light has not reached us yet, or because it never will. Accelerated expansion, confirmed by observations of distant supernova and by data from the cosmic microwave background, tells us something even more subtle. Over time, the region accessible for the exchange of information will actually shrink. This leads to the concept of a cosmological event horizon, similar in principle to the event horizon of a black hole, but spanning an entire universe. At a certain point, distant objects will recede faster than light can reach us, not because they are breaking physical laws, but because space itself is expanding. The objects do not move faster than light. The distance between points in space increases. One hypothesis suggests that the edge of the universe is not a physical edge at all, but a boundary of causality, a region from which no information can ever reach us. No, not in the future. This limitation is built directly into the structure of space-time itself. In THCS view, the universum system where the ultimate boundary depends on who is observing and from where. A civilization located in another part of the cosmos would have its own observable universe. Regions hidden from us could be perfectly visible to them. There is also the possibility that the universe is infinite in spatial extent. If so, the idea of an edge becomes meaningless. Yet, even an infinite structure can still be finite in what can be observed. Imagine an endless plane stretching forever, but illuminated only within a certain radius. Everything beyond the light does not cease to exist. It simply remains unreachable to the observer standing at the center. This analogy helps clarify the nature of the observable universe. It is limited not by a true ending, but by our position in time. We must also consider the uneven distribution of matter and energy. In the early universe, regions of different density evolved at different rates, shaping the large-scale structure we see today. Even if a region is so distant that its light will never reach us, it may still influence the universe as a whole. For example, the distribution of dark energy, which governs the expansion of space, could be affected by processes occurring far beyond our observational horizon. Some cosmological models allow for unusual geometries. The universe may be open, flat, or closed. In a closed universe, space resembles the surface of a sphere, not into dimensions, but in three. Such a universe has no edge, yet possesses a finite volume. Travel far enough in one direction, and eventually you would return to your starting point. After an unimaginably long journey. In flat or open universes, space may be infinite, but measurable regions remain limited by our horizon. There are even more speculative ideas. Some theories suggest a multiverse, where our universe is only one region within a much larger structure. In this scenario, the edge might be a boundary where our region meets others, with different physical laws, different constants, different histories of expansion. For now, such ideas remain beyond direct testing. No observation has confirmed interactions between different cosmic regions or bubbles. Still, these concepts are discussed because they may help explain subtle features of the cosmic, microwave background, and the distribution of matter. No matter how we describe the structure of the cosmos, one principle remains unchanged. Any idea of an edge depends on what we mean by access to information. Light limits what we can see. Gravity limits what we can influence. Expansion limits what can ever exchange signals with us. So the edge of the universe is not a fixed line. It is a dynamic boundary shaped by physical laws and cosmic evolution. This complexity deepens when we realize that the observable universe and the true scale of cosmic space are not the same thing. We tend to believe that what we see reflects reality directly. In cosmologie, the light reaching telescopes today was emitted when the universe looked very different. When we observe distant galaxies, we are not looking across space alone. We are looking through time. This creates the illusion of a fixed boundary. In truth, what we see is a temporal horizon. There are two key horizons that help describe the observable cosmos. The first is the particle horizon, the maximum distance from which light could have reached us over the entire history of the universe. It defines the sphere of the observable universe, with a radius of approximately 46 billion light-years. And beyond that quiet limit, the universe may continue, vast, silent, and forever beyond reach. If we put this number into words, we are speaking of 46 billion light-years in one direction. Across the full diameter, it becomes more than 90 billion light-years. Such a value does not fit into ordinary ideas of size or distance. It resists intuition, yet it follows directly from the geometry of an expanding space itself. The second horizon is the event horizon, the boundary beyond which processes will never be able to influence us in the future. Unlike the particle horizon, which is connected to the past, the event horizon is connected to what is yet to come. Its existence is caused by the accelerated expansion of the universe. If a region of space moves away from us faster than light can cross the ever-stretching distance, signals from that region will never reach an observer. Not now, nor ever. In this way, the event horizon limits what can possibly be seen or known. Boundary in principe, these are inside, and neither of them represents a physical wall. One cannot fly a spacecraft toward the particle horizon and discover a tear, an edge, or a cliff in space. This boundary exists only as a mathematical limit of observation. It depends on the history of cosmic expansion and on how far light has managed to travel. Because of this, the size of these horizons was different in earlier epochs of the universe, and in the distant future their scale will change again. Understanding the nature of these boundaries helps explain why the idea of a literal edge of the universe can be misleading. We can observe only the part of cosmic space that has had time to interact with us. If we compare this to standing outside on a foggy night, our circle of visibility limits what we can perceive. But it does not limit the landscape itself. Everything hidden in the fog continues to exist, whether we can see it or not. In cosmologie brève, the finite speed of light and the expansion of space, there is a hypothesis that beyond the observable region, the structure of the universe remains similar to what we see within it. A vast cosmic web of filaments and voids, forming enormous clusters of galaxies. These filament-like structures stretch across hundreds of millions of light years. When spoken aloud, this means distances of hundreds of millions of light years in every direction, according to cosmological models. There is no clear reason to assume that something fundamentally different lies beyond the observable sphere. However, there is also no direct data, and likely never will be. Some researchers suggest that the universe may possess curvature. Even slight deviations from perfect flat geometry can cause distances and parallel paths to behave in unfamiliar ways. For example, in a closed universe, light could travel around a vast cosmic loop and eventually return to the region where it was emitted. This creates a fascinating scenario in which the same galaxy could be visible in different directions, not because of reflection, but because of the shape of space itself. However, current observations show that the universe is extremely close to flat, at least within the limits of what we can observe. If we imagine the edge of the universe as a finite physical boundary, we encounter contradictions with what we know about the cosmic microwave background. This radiation, formed shortly after the first atoms appeared, is distributed across the sky with remarkable uniformity. Its temperature varies only by tiny fractions of a degree. Such uniformity suggests that the early universe was highly homogeneous. If a physical boundary existed, one that restricted the flow of matter or radiation, traces of this boundary should appear as irregularities in the background. But no such global anomalies are observed. At the same time, the observable universe does contain features that inspire speculation about regions beyond it. One example is the so-called cold spot. In the cosmic microwave background, it spans a vast area of the sky and has a temperature lower than average. Some scientists have suggested that this cold spot might be the result of interaction with another region of space, possibly even another bubble of cosmic expansion. Yet there is no direct evidence for this idea. More conventional explanations, such as statistical fluctuations or the influence of large-scale structures, remain more likely. The question of whether the universe has an edge is closely connected to the nature of inflation, a period of extremely rapid expansion that occurred in the earliest moments of cosmic history. Inflation may have stretched space so dramatically that the observable universe is only a tiny fragment of a much larger, perhaps infinite, whole. If expansion occurred unevenly, regions could have formed where the properties of space differ from ours. Some models suggest that inflation produced independent regions, each with its own values of fundamental physical constants. In this context, the edge of the universe becomes no a physique à surface, but a boundary of possible physical conditions. The nature of cosmic horizons creates a quiet paradox. We observe light emitted more than 13 billion years ago, yet it reaches us from distances exceeding 40 billion light-years. This mismatch arises because space itself expanded, while the light was traveling. Observing distant regions therefore reveals the past, while simultaneously hinting at the immense scale of the present-day cosmos. Another subtle consequence is that the boundary of the observable universe expands with time. Et very second, new regions become visible as their light reaches us. At the same time, accelerated expansion creates regions that gradually disappear from the reach of any future observer. This makes the idea of the universe's edge dynamic. The boundary never remains fixed. We live inside a sphere whose size is determined not by technology, but by the fundamental properties of space itself. This sphere is not permanent. Its scale changes with the age of the universe. Inside it lies everything we can observe or measure. Beyond it lies what is hidden, not because it does not exist, but because it cannot interact with us. The idea of a physical edge to the universe raises many questions, because any limitation of space must have a cause. One cannot simply imagine the cosmos ending abruptly. If a surface existed separating our space from nothingness, its nature, composition, origin, and interaction with its surroundings would all require explanation. Such constructions contradict cosmological principles, in which space does not need support, walls, or a container. Still, the hypothetical edge remains a valuable thought experiment, a way to explore how the cosmos behaves under different conditions, and as the universe continues to expand, quietly and endlessly. The question remains open, not as a wall to be reached, but as a horizon that moves. As time itself flows on, some models suggest that space itself may have a specific shape, defined by its internal geometry. In a closed system, similar to a three-dimensional sphere, there is no edge. Yet, the volume is finite. Insuffisamment into it. If one were to travel long enough in a single direction, it would be possible to return to the starting point, although the journey would span an incomprehensibly vast distance. The hypothesis of closed geometry is appealing because it removes the need for a physical edge, while still allowing the universe to have finite dimensions. However, observations of the cosmic microwave background indicate that the curvature of space is extremely small, and if the universe is closed, its radius is so enormous that any cyclic nature becomes practically impossible to detect. There is also the idea that the edge of the universe could appear as a region where the laws of physics themselves change. For example, constant is that particle might take on different values. In such scenarios, the edge represents a boundary between two regions formed during inflation. In une région par un way, in another differently. This concept views the edge not as a material wall, but as a transition between physical regimes. Yet, we see no hints of such transitions. Within the observable cosmos, the temperature of the cosmic microwave background and the distribution of galaxies do not display persistent anomalies that would indicate crossing into another region. Observations of large-scale structures suggest that surrounding space behaves quite uniformly. Across immense distances, galaxies form filaments, nodes, and voids, creating a vast cosmic web. This structure repeats on scales of tens and hundreds of millions of light years. When expressed in words, this means tens of millions of light years for the smallest connected structures, and hundreds of millions of light years for the largest complexes beyond the observable region. This structure may continue endlessly, either preserving the same patterns or gradually transitioning into areas where matter density slowly decreases. Some versions of inflationary theory allow for the existence of enormous regions formed in a largely random way. These regions may exceed the observable universe by many orders of magnitude. In this case, the edge we can speak of is not a geographical boundary, but a transition between inflationary bubbles. If we imagine space as foam, where each bubble expands and exists independently, our bubble has its own domain, and neighboring bubbles have theirs. Interaction between bubbles is theoretically possible, but extremely unlikely because the distances between them grow faster than light can traverse. Another approach to the question of boundaries relies on the concept of expanding space itself. In this model, the edge in whose radius is so great that no signal from it will ever reach us, even with infinite waiting. This is not the cessation of existence, but the cessation of connection. Everything beyond a certain distance moves away faster than light, due to the stretching of space. Thus, the edge in this interpretation is a limit of causality, not a physical barrier. This limit can be defined mathematically, but it changes over time because expansion is accelerating. An important point to understand is that space is not an empty stage. It is a dynamic medium, capable of stretching and evolving. If the universe is infinite, then it has no edge in the traditional sense. Nevertheless, observable space remains limited by the particle horizon, and this horizon, regardless of scale, reveals only a small fraction of what may exist beyond. Calculations suggest that beyond the observable sphere, there may be an enormous number of galaxies, tens or even hundreds of times more than what we can currently observe. In words, this means that if we see hundreds of billions of galaxies, their total number may reach trillions, or far beyond. Hypotheses involving a physical boundary almost always encounter the same problem. What lies beyond it? If there is absolute emptiness, no space and no time, then one must explain how this emptiness interacts with our region. If, instead, there is another form of space that remains unobservable, then the concept of an edge becomes conditional. The boundary turns into a transition between causally disconnected regions. To describe such systems, physics uses mathematical models, but they remain highly theoretical. Some scientists discuss the possibility that the edge could be related to quantum properties of space. If space is considered as a collection of quantum cells at the Planck scale, then limits defined by quantum gravity may exist. Such limits could determine which regions of space can arise during expansion and which cannot. However, a complete theory of quantum gravity does not yet exist. For this reason, these ideas remain hypothetical. It is also important to consider the principle of cosmological homogeneity. This principle states that, on sufficiently large scales, the universe is the same in all directions. If this principle holds, then a physical edge cannot exist, because it would violate homogeneity. Only infinite or closed space satisfies this condition. There are also intellectual attempts to describe the edge through topology. Space may possess a complex, multiply connected structure, where movement in a straight line leads into other regions through spatial identifications or wormhole-like connections. In such mode, the edge is not a point exists permanent, but appears a network of paths that do not lead outward. These models are extremely difficult to visualize, yet they show that the geometry of space may be far stranger than it appears at first glance. Reflecting on the idea of an edge once again leads to the understanding that the boundary of observation and a physical limit are not the same thing. What we cannot see or measure does not have to be finite or ending. The cosmos may have no end and no beginning in the traditional sense, yet still remain limited for us by the laws governing signal propagation. The idea of an edge to the universe inevitably forces us to understand not only its structure, but the very mechanism by which space expands. Unlike motion through an ordinary medium, cosmic expansion does not mean that galaxies are flying through emptiness at increasing speeds. Instead, the fabric of space itself increases its scale, and distances between objects grow independently of their local motion. Galaxies may remain almost stationary within their own regions of space, yet the distance between them still increases. This is the key idea that transforms our classical understanding of limits and boundaries. One of the most common misconceptions is the idea that the universe is expanding into some external space. Modern models show something very different. It is space itself that is expanding, not objects moving outward into emptiness. There is no outer shell into which the cosmos grows. There is no void beyond the boundaries, waiting to be filled. The geometry of expansion is woven directly into the structure of the universe itself. Because of this, the question, what lies outside the universe, loses its meaning. Outside simply does not exist, because the concept of outside applies only to already existing space. The nature of expansion becomes especially clear when we observe distant galaxies. The farther an object is from us, the faster it recedes, not because it is moving through space, but because the space between us is stretching. This relationship was discovered in the first half of the 20th century and later confirmed with precise measurements. Yet, it is crucial to understand that increasing recession speed does not violate the cosmic speed limit. Galaxies are not racing through space faster than light. They are carried along with space itself. For this reason, relative recession speeds can exceed the speed of light without contradicting physical laws. If we think about expansion this way, a natural question arises. Is there a point where this recession reaches a maximum, and what would such a point mean? Models show that no fixed boundary exists where expansion suddenly stops or changes its nature. On large scales, space expands uniformly. And so, if we imagine an edge as a place where expansion ends, such an edge does not exist. A boundary appears only as a mathematical consequence of limited observability. Of special interest here is the concept of the metric. It describes how distance is measured depending on the properties of space itself. In an expanding universe, the metric changes over time. This means that the distance between 2 points increases even if those points are not moving physically. Imagine a two-dimensional surface with dots drawn upon it. As the surface is gently stretched, the dots drift apart without sliding across the surface. This simple image helps us understand how space influences distance on the scale of galaxies and even larger cosmic structures. A key component of cosmic dynamics is dark energy. Its nature remains unknown, but observations show that it drives accelerated expansion. Its influence grows as the volume of space increases. The more space there is, the stronger the effect of dark energy becomes. This creates a gradual cosmic acceleration, a quiet, steady speeding up of the universe. In the early epochs, expansion slowed under the pull of gravity. In the present era, the pace increases. Accelerating expansion creates boundaries that are not physical barriers, yet carry deep meaning for our understanding of limits. If a region of space recedes so rapidly, that light from it will never reach us. That region becomes forever inaccessible. We may assume that similar processes galaxies forming, star burning but can never arrive. This is why discussions about the edge of the universe are always linked to the concept of the event horizon. When expansion is evaluated through spatial curvature, we find that the universe is extremely close to flat. This means its geometry does not cause paths to curve back onto themselves. In other words, space does not bend enough to close in on itself. This is an important result. In a closed geometry, an edge does not exist by definition. Space would be finite, but without a boundary. In a flat or open universe, an edge also does not exist, but space may be infinite. If we hypothetically assume that the universe is infinite, an interesting question arises. How can one speak of an edge in an infinite system? In this case, it becomes a limit of perception and information access. An infinite space may contain an infinite number of galaxies, yet only a finite region will ever be observable. Here, the edge is the boundary of what we can see, measure, and analyze. It becomes subjective, dependent on the observer's position. Some cosmologists treat expansion as a fundamental property of spacetime, requiring no external explanation. But in deeper models, especially those involving quantum gravity, mechanisms may exist that determine the parameters of expansion. In such models, space itself may be a dynamic object composed of elementary quanta. If space has a discrete structure, at Planck scales, expansion could result from transitions between quantum states. In this context, the idea of an edge gains another meaning as a limit beyond which macroscopic geometry no longer applies. There is also a hypothesis that expansion may cease in certain regions. In Sushma des Minius, with different areas expanding at different rates. In non-region accelerates. In another, it remains nearly constant. However, such scenarios currently lack observational support. The observable universe displays is a very high degree of isotropy on average. It looks the same in all directions. Another intriguing aspect is the possibility of density fluctuations on extremely large scales. If regions beyond our observable domain possess different densities of matter and energy, their influence might appear indirectly through global cosmological parameters. For example, variations in dark energy distribution could alter the rate of expansion, but such effects are extraordinarily difficult, perhaps impossible, to measure directly. In discussions of expansion, a frequent question arises: how can space stretch? If nothing can move faster than light, the key is this: the speed limit applied to objects moving within space. It does not apply to changes in space itself, just as stretching a rubber band increases the distance between 2 points, even when the points themselves remain still. Thus, reflection on cosmic expansion shows that the edge of the universe cannot be imagined as a fixed boundary, separating existence from nothingness. The edge does not exist as a physical place. It exists only as the quiet limit of what can ever reach us. It exists only as a limit, emerging from the delicate relationship between light, time, and geometry. The idea of an edge of the universe requires careful clarification. The word edge can refer to very different levels of physical limitation. If we imagine space as a three-dimensional extension, a natural question arises: can there be a point beyond which space simply does not continue? In classical geometry, an edge is a boundary where space comes to an end. But in modern cosmology, this interpretation no longer applies. Spacetime, as described by general relativity, is not required to have a geometric boundary. It may be infinite in extent, or finite, yet without an edge in the familiar sense. Physicists describe space using the concept of a manifold, a mathematical structure whose surface may curve, close in on itself, or expand endlessly. A simple two-dimensional analogy helps here. The surface of a sphere has no edge, yet it has a finite area. An observer traveling across this surface can move forever without encountering a boundary. This analogy offers insight into the possible three-dimensional curvature of our cosmos. If the space of the universe is closed, it possesses a finite volume without borders. However, modern measurements of matter and energy density indicate that the geometry, at least within the observable region, is extraordinarily close to flat. Tilly Vopen, the possibility of infinite space, while not completely excluding a slightly closed configuration, whose radius is so immense that curvature becomes practically invisible, rather than searching for a physical edge. Cosmologists focus on limits imposed by the laws of nature. En sus limite is the speed of light. It defines the maximum rate at which information can travel. Because distances in the universe increase due to cosmic expansion, this speed sets a boundary on what can ever be accessible to us. Edges defined by the speed of light are not features of space itself, but limits of causal interaction, théarchapèdes, by the history of cosmic evolution. Light has been traveling for more than 13 billion years, yet space has expanded so dramatically that the radius of the observable universe is now about 46 billion light-years. This reveals how expanding space and the finite speed of radiation combine to form a dynamic structure of accessibility, an edge in an informational sense. Another type of boundary is defined by the event horizon. It is a region of spacetime beyond which events can never influence an observer. In cosmologie, this horizon is closely linked to dark énergie. Dark energy is a form of energy that fills space uniformly. It drives accelerated expansion. À sa résulte, some regions of space recede so rapidly that no signal from them can ever overcome the growing distance. The cosmological event horizon is not a physical wall, idealin, separating the possible from the unreachable. Events occurring within this boundary may eventually become visible. What happens beyond it remains forever hidden. The concept of an edge grows more complex because spacetime itself is dynamic. Its properties change over time. Cosmological models show that in the early universe, distances increased at an extraordinary rate. This phase is known as inflation. Inflation stretched space to immense scales in an unimaginably short moment. À sa résulte, the region we observe today represents only a small fragment of the space that once expanded. If inflation lasted long enough, the universe may have grown to nearly limitless size. In that case, any edge, if it exists at all, lies so far away that it cannot be described within observable physics. If we view space as a collection of causal regions, each region possesses its own observable boundary. Imagine a vast system made up of countless spheres, each defined by its own particle horizon. These spheres are not physical objects. They are determined by which events can be observed from a specific location. Thus, to observers in different parts of the cosmos will have different observable limits. What lies beyond our sphere of visibility may well fall within the visible domain of another observer. This makes the idea of an edge relative. It depends on position, cosmic epoch, and the dynamics of expansion. A particularly intriguing question is whether the universe could possess a global edge that exists physically. Some exotic models allow space with a boundary. There are mathematical constructions in which space is finite and has an edge, yet neither light nor matter can interact with it due to geometric constraints. In sus mode, the edge exists as a topological feature completely hidden from observation. It cannot be reached because geodesic paths, the natural trajectories of particles, never lead to it, while most standard models exclude a physical edge. Not all theoretical approaches agree. Some concepts propose that space may resemble a bubble, surrounded by regions with different physical properties. This idea appears in certain versions of multiverse models. If our cosmic region emerged through a quantum transition from a more fundamental state, its edge could represent a boundary of phase change. However, such models cannot be tested from within our universe because signals from these boundaries cannot penetrate the immense stretching caused by inflation, shifting from geometry to energy considerations. The edge may also relate to the distribution of energy density. Some models predict that dark energy density could vary with position. These ideas are rare, but they are explored. If energy density changes significantly in a particular direction, the properties of space, such as expansion, rate, or curvature, would also change. In this case, an edge might be defined as a transition zone between regions with different physical parameters. However, observations of the cosmic microwave background reveal extraordinary uniformity, placing strong constraints on such possibilities. A physical interpretation of the edge must therefore also consider the nature of the spatial metric, the quiet framework that determines how distances, time, and geometry are woven together in the universe. A métrique is the way distances are measured within space itself. In an expanding universe, the metric is constantly changing. Because of this, the distance between 2 points may increase, even if there is no motion between them in the familiar sense. This greatly complicates the question of reaching an edge. One cannot simply travel in a chosen direction and expect an edge to appear as a boundary of space, because the metric itself evolves. The path a spacecraft would need to cross continually grows longer. À sa résulte, the edge may be unreachable, not because it lies unimaginably far away, but because space stretches faster than any object can move through it. One of the key concepts shaping our understanding of the edge is the idea of the cosmic horizons, the horizon of the past and the horizon of the future. The past horizon defines the limit of what can be seen. the future horizon, defines the limit of what can ever be influenced. Touche terre. These two horizons form the fragment of the universe that is accessible to us in both time and space. Beyond them, processes may serve unfold that we will never observe and never affect. If we imagine these horizons as forming a surface, they may be interpreted as the boundary of our cosmic existence, intessence, the edge of the limit of observation, a limit of causality, a limit defined by the metric, or a limit of physical structure. Different cosmological models describe this boundary in different ways. For some, it does not exist at all. For terre, it is hidden by geometry. For some, it is tied to phase transitions. For others still, to inflationary processes. Yet, for any observer living inside the universe, the edge, in a physical sense, remains unreachable and cannot be directly defined. Information about it is accessible only through mathematical models and indirect traces left by the evolution of space. Debates about what lies beyond the observable universe have continued for decades. Our telescopes push the horizon outward, but these limits remain constrained by the speed of light and the expansion of space. We can form hypotheses, analyze the cosmic microwave background, study the distribution of galaxies. But Lofty offers only indirect clues. The question of what exists beyond the visible world belongs to a class of problems where science must rely on mathematics and probability. One widely discussed hypothesis suggests that beyond the observable universe, the familiar structure of the cosmos continues. The same large-scale cosmic web, galaxies, clusters, and filaments, stretching across unimaginable distances. In this view, the observable sphere is merely a small region of a much larger whole. If the cosmos is infinite, the boundary we see is a temporary illusion. Light from those distant regions has simply not yet reached us. Those regions may exist under the same conditions as our part of the universe. Interasciescas. No special structures or physical barriers are required. The boundary arises solely from the limits of perception. Another hypothesis proposes that beyond the observable region there may exist areas with different matter densities and different histories of structure, formation. Irregularities in the early universe could have caused processes to unfold faster in some places and more slowly in others. As a result, regions may have formed where galaxies developed differently and dark matter was distributed in unique way. We cannot test this directly, but mathematical models allow for such possibilities. If we could travel far enough we might observe subtle differences in cosmic structure, even if those differences were faint. An intriguing idea suggests that inflation itself may have been uneven. If inflation proceeded at different rates in different regions, areas could have formed where the properties of space and even fundamental parameters differ from those we observe. Some models allow physical constants to take on different values in other regions, the rate of expansion, the masses of elementary particles, or the strength of interactions. These regions may have emerged as independent domains during early expansion. In sa view, the boundary of the observable universe becomes a frontier between regions with different sets of physical parameters, though there is no direct evidence for this idea. Another fascinating hypothesis suggests a vast diversity of regions beyond our horizon. Space is enormous, or infini. It may contain regions similar to ours, yet shaped histories. In infinite space, the distribution of matter could be such that far beyond our view, there exist areas containing structures analogu or even identical to those we see here. This does not imply mystical copies or parallel worlds. It follows from statistical reasoning. In infinite space, any configuration of matter not forbidden by physical laws can occur. Some researchers propose that beyond the observable universe, there may exist zones dominated by processes we cannot perceive due to scale and distance. For example, a region with slightly higher dark energy density could influence the global properties of the cosmos. Dark energy appears uniform, yet models allow for very small fluctuations which, over vast scales, could alter the expansion rate. Such variations would be invisible within our observable region, but might shape unique properties tens of billions of light-years away. This makes possible the existence of regions where expansion proceeds faster or slower than the cosmic average. There is also a hypothesis that beyond our horizon lies the continuation of the inflationary field. If inflation did not end everywhere at the same moment, there may exist regions where it continues even now. These regions are known as eternal inflation. They are unobservable, yet their existence follows from certain solutions to equations describing the early universe. If this hypothesis is correct, beyond the observable universe, there may be regions where space expands at a rate utterly unreachable today. In such regions, galaxies, stars, and planets cannot form. They remain sparse, stretching endlessly at extraordinary speed. In this case, the edge of the observable universe becomes a boundary between ordinary cosmos and an inflationary domain. Finally, there are ideas suggesting that beyond the visible world lie structures we do not yet know how to describe. If space possesses a complex global topology, it may be finite and closed yet lack an edge in the usual sense. In such a universe, traveling in one direction forever would eventually return you to your starting point. This idea is compelling, as it may help explain certain features of the cosmic microwave background, although there is still no direct evidence for a closed topology. If such a structure does exist, then the edge of the universe does not exist as a physical category at all. Any boundary becomes only a limit of observation. Some models suggest the existence of what is called superhorizon Augean, an area from which disturbances may arise that influence the large-scale structure of our cosmos, yet remain inaccessible to direct observation. Such disturbances could have produced small anomalies in the temperature distribution of the cosmic microwave background, or subtle asymmetries that are difficult to explain using only internal processes. These models do not claim the existence of a physical edge. Instead, they suggest that our region is part of a much larger structure, whose dynamics are shaped by factors lying beyond the observable sphere. One of the boldest ideas proposes that beyond our horizon, there may exist many other bubbles of cosmic expansion. If inflation created not one, but countless regions expanding independently, then our universe would be only one such bubble. Between these bubbles, there may have been zones of contact or even collisions. Their traces, however, are extremely difficult to detect. Some scientists have searched for specific circular patterns in the cosmic microwave background that might hint at interactions between neighboring bubbles. So far, no convincing evidence of such structures has been found. Even so, the theory remains a subject of discussion because it naturally explains the diversity of possible regions of space. There are also approaches that suggest the existence of regions where the properties of spacetime itself differ so strongly that an entirely different geometry may apply. Such regions might contain other forms of symmetry or alternative distributions of energy. These ideas belong more to theoretical exploration than to testable hypotheses. Their value lies in expanding our imagination of what cosmic structure might allow, even if observation cannot yet confirm them. The essence of all these approaches is the same. The edge of the observable universe may simply be a boundary of knowledge, not a physical structure. We observe only the portion of the cosmos that has had time to establish contact with us. Beyond that limit, there may exist a diverse and complex realm, filled with processes we cannot see, yet which may shape the global properties of all cosmic space. The idea of a physical edge implies the existence of a surface or structure beyond which there is no space, no time, no matter. This seems intuitive on a human scale, yet most cosmological models exclude this possibility. Space can be finite without having an edge. This property often feels paradoxical, but it follows naturally from geometry. A three-dimensional space can be limited without possessing a boundary. The analogy of a sphere helps illustrate this idea. The surface of a sphere has a finite area, yet no edge, because every point connects continuously to its neighbors. The geometry of the universe is determined by curvature, and three possibilities exist. Positive, 0, onde neg. Positive curvature corresponds to a closed universe. Zéro curvature corresponds to flat space. Negative curvature describes a hyperbolic geometry. If the universe has positive curvature, it may be finite, and yet boundless. Over. Measurements of the cosmic microwave background show that curvature is extraordinarily close to zero. T suggest that space is either infinite or sud-ouest vaste, that its closed nature, l'effarbillon, our observable reach. Some hypotheses explore topologically complex models. In these models, space may take the form of fatorus, multi-connected structures, or other closed configurations. In such scenarios, the universe could be finite, yet structured so that traveling far enough in one direction would eventually return you to your starting point. This resembles video game worlds where exiting one edge of the map bring you back from the opposite side. In cosmology, however, this would be a natural consequence of topology, not artificial rules. If such structures exist, certain regions of space might be visible in multiple directions. So far, no observations confirm Such-feuature, the idea of a physical boundary, faces serious challenges at the level of physical laws. If we assume a place where space simply ends, where dusk, what happens to particles approaching this boundary? Do they stop, reflect, or vanish? Each possibility requires additional laws unsupported by observation or theory. Spacetim, as described by general relativity, does not allow such abrupt endings. There are hypotheses suggesting that an edge might correspond to a transition, interregion, where physical laws take different forms. These ideas arise in the context of the multiverse. Et pour univers, une région within a larger structure, its edge might be a zone of contact with other regions. Such transitions, Kuldbesmut, or abrupt, depending on how inflation unfolded elsewhere. Yet no observational program has revealed evidence of such encounters. Maps of the cosmic microwave background have been analyzed repeatedly. But no signe of collision between expanding bubbles have been found, even though inflationary theory allows for many independent regions, each with its own properties. This does not imply the presence of a physical boundary within our region. Our cosmic domain may be autonomous en devaster nous, to expand indefinitely, without interacting with neighboring regions. 2. Even if a multiverse exists, the boundaries between regions may lie so far away that their influence is completely beyond observation. Particular interest surrounds the idea that an edge might be linked to the quantum structure of spacetime itself. At extremely small scales, near the Planck length, space may lose its classical properties. Some models suggest that topology may fluctuate and geometry itself may change. However, these effects occur on scales utterly negligible compared to cosmic distances. If an edge exists at this level, it has no relevance to the vast expanses studied by cosmology. For an edge to exist physically, one must assume that space can truly end. But within general relativity, spacetime is described as a smooth four-dimensional structure whose evolution is governed by the distribution of matter and energy. And within this framework, space does not simply stop. It flows, curves, expands, without ever meeting a wall. This structure does not allow for interruptions. If an artificial boundary were introduced, it would require new physics beyond all known laws. Theoretically, such an approach is possible, but it is not supported by data and would demand mechanisms so complex that they go far beyond what observation suggests. Some researchers consider the idea of a finite universe through the lens of the anthropic principle. This principle suggests that we observe the universe not because it is the only one possible, but because it allows observers to exist. If space contains enormous, perhaps countless, regions, only some of them would possess parameters suitable for forming structures like galaxies, stars, and eventually observers. In this context, the idea of an edge loses its fundamental meaning. It becomes a relative concept existing only within a local domain. Another important aspect is that even a finite universe with closed geometry may be so vast that it appears infinite to us. If the radius of curvature exceeds the observable region, no measurement could reveal the true global shape. We could be living inside a closed space without ever discovering it. The observed uniformity of the cosmic microwave background indicates that if curvature exists at all, it is extremely small. This allows for the possibility of a closed universe, but does not point to the presence of an edge. As a result, scientific models tend to replace the concept of an edge with the concept of a limit of observation. What we call the edge of the universe is, in reality, the boundary beyond which light has not had time to travel. This does not mean that nothing exists there. Beyond our horizon, there may be structures of any complexity, galaxies, clusters, vaste voies, dark matter, regions with different densities. All of this may exist in full richness and order. It remains inaccessible, not because it is absent, but because information from there does not reach us and never will. The idea of a physical edge encounters many limitations: observational, theoretical, geometrical, Most cosmological models agree that even if the universe is finite, its surface has no rupture. It forms a closed structure, without borders in the usual sense. And if the universe is infinite, then, speaking of an edge, has no meaning at all. There is no wall. No ending les lips. There is only a horizon, soft, distant, defined light, time, and the slow breathing of expanding space. En beyond, not emptiness, silence. A silence that exists not because nothing is there, but because it cannot speak to us. And in that silence, the universe continues, quietly, endlessly, whether we are able to see it or not.